There's a 4.35-ton stone statue standing on Easter Island today that, according to a 2025 study using physics, 3D modeling, and a full-scale replica, was never dragged across the ground, never rolled on logs, and never hauled flat on a wooden sled. It walked there, upright. A small team pulled ropes from alternating sides, gently rocking the enormous statue back and forth. With each controlled shift of its weight, the stone pivoted forward by another small step. Again and again, the same motion carried several tons of solid rock across the island, without the statue needing to be lifted or dragged. It sounds impossible, until you realize it's only one example of something ancient humans mastered again and again. How did ancient humans, living in completely unrelated cultures, separated by oceans and thousands of years, build and move some of the heaviest structures on Earth, using little more than rope, wood, stone, water, and coordinated human effort? No cranes, no trucks, no hydraulics, no electricity. What they had instead was human coordination and a practical understanding of how the physical world behaved. They may never have written equations explaining friction, leverage, momentum, or buoyancy, but they understood what happened when sand was wet, when weight was shifted onto a pivot, when stone was placed on a sledge, or when water was allowed to carry a load too heavy for people to move efficiently on land. And sometimes, solving these enormous problems required entire societies to organize themselves around a single shared goal for years. The answers take us from wet sand beneath Egyptian sledges to stones transported across ancient Britain, and finally to statues that may have literally walked across Easter Island. But to understand how ancient people accomplished the seemingly impossible, we should begin with the most famous construction project in human history, the Great Pyramid of Giza. Even today, the scale is difficult to fully grasp. The Great Pyramid contains more than 2.3 million stone blocks. Many weigh several tons, while some of its largest stones are dramatically heavier. They were quarried, transported, raised, and positioned with extraordinary precision. And the result is still standing more than 4,500 years later. It survived wars, earthquakes, sandstorms, and thousands of years of weathering. Yet one of the first things we need to correct is the popular image of how it was built. For generations, people imagined enormous armies of enslaved workers being forced to construct the pyramid under brutal conditions. Archaeological evidence paints a more complicated picture. Evidence from settlements near Giza, combined with surviving records connected to pyramid construction, points toward a highly organized labor system involving skilled workers and rotating crews, supported by a much larger logistical network. Thousands of people were needed not only to quarry and move stone, but also to manufacture tools, prepare food, transport supplies, maintain infrastructure, and keep the entire operation functioning. The Great Pyramid, then, wasn't built by strength alone. Its real foundation was organization. Imagine coordinating thousands of people toward one goal without computers, engines, modern vehicles, or digital communication. Food had to arrive, tools had to be replaced, stone had to be quarried, transport routes had to remain functional. Workers had to know exactly where to go and what to do, day after day, year after year. The pyramid itself is impressive, but the invisible logistical machine behind its construction may be just as remarkable. Still, one enormous question remains: how did they actually move the stones? The simplest answer is that ramps almost certainly played some role, but exactly what those ramps looked like remains debated. For decades, one popular image involved a gigantic straight ramp extending from the ground toward the upper levels of the pyramid. The problem is scale. A ramp capable of reaching the pyramid's highest levels at a manageable slope would itself have been an enormous construction project. So researchers have explored alternative possibilities. One of the most famous was proposed by French architect Jean-Pierre Houdin. Houdin became fascinated by a hypothesis developed by his father and eventually devoted years to investigating the pyramid's construction through architectural analysis and computer modeling. His solution, became known as the internal ramp theory. According to this idea, builders may have used an external ramp during the early stages of construction, then transitioned to a ramp spiraling upward within the growing structure itself. Instead of building one impossibly massive ramp stretching far into the desert, workers could continue hauling stones upward through corridors winding around the pyramid's core. It is an elegant possibility, and it offers a potential explanation for why archaeologists have never discovered the remains of a gigantic external ramp capable of reaching the pyramid's summit. But the exact construction method remains debated. What we do know is that the Egyptians were extraordinarily skilled at turning difficult transportation problems into manageable ones. One of their greatest advantages may have been water. Ancient branches of the Nile once reached much closer to the pyramid complexes than the modern landscape suggests. This meant stone could be transported by boat for much of its journey. Instead of dragging enormous blocks across vast stretches of dry land, workers could allow water to support the weight. Then human muscle was needed primarily for the final stages of transportation. And once the stones reached land, the Egyptians had another surprisingly effective trick: wet sand. Ancient Egyptian imagery depicts workers pulling heavy loads on sledges while someone pours water onto the sand ahead of them. For a long time, the significance of this detail wasn't fully appreciated. But modern experiments have demonstrated the underlying principle. Dry sand can pile up in front of a moving sledge, increasing resistance. Add the right amount of water, however, and the grains bind together more effectively. The surface becomes firmer. The sledge moves more easily. The amount of pulling force required can fall significantly. The Egyptians didn't need to understand the microscopic physics involved. They didn't need an equation to recognize what worked. Pull a heavy object across dry sand. Then try again after adding water. If one method requires fewer people and less effort, you remember it. Then you teach the next crew and the next generation. That is one of the most important ideas in ancient engineering. Knowledge didn't need to begin with theory. It could begin with observation. Experiment, observe the result, and preserve whatever worked. Over generations, practical experience becomes technology. Now leave the Egyptian desert behind and travel thousands of kilometers north to a windswept plain in southern Britain. Stonehenge presents a different version of the same fundamental problem. How do you move something that seems too heavy to move? Some of Stonehenge's largest stones weigh tens of tons. But raising them at the construction site was only part of the challenge. Some stones had traveled extraordinary distances before reaching Salisbury Plain. The monument's bluestones have been linked to sources in Wales, meaning prehistoric communities somehow transported multi-ton stones across a journey spanning hundreds of kilometers. There were no modern roads, no trucks, no cranes. So how was it done? The precise routes and methods remain debated, but researchers have proposed combinations of overland hauling and water transport. On land, stones could be moved using sledges, ropes, wooden tracks, rollers, or combinations of these technologies. Where rivers or coastal routes were available, water may have offered another possibility. Once again, the principle is simple. Don't fight the entire weight if nature can carry part of it for you. Water is exceptionally good at supporting heavy loads. A stone that is brutally difficult to drag across uneven ground becomes a very different transportation problem when placed on a sufficiently stable vessel. Whether every Stonehenge stone followed such a route remains uncertain. But the broader principle appears repeatedly throughout ancient engineering. Use the landscape, use gravity, use water, reduce friction, and never waste human strength solving a problem nature can solve more efficiently. Once the stones reached their destination, another challenge began. How do you make a multi-ton stone stand upright? You don't necessarily lift the entire thing vertically in one enormous movement. Instead, you change the problem. Dig a prepared hole. Position the base. Use ropes and wooden levers. Raise one side gradually. Shift the center of gravity. Rock, pull, brace, repeat. The impossible single movement becomes a sequence of smaller movements. Instead of defeating gravity, you negotiate with it. That idea, breaking one overwhelming task into many manageable steps, appears again and again in ancient construction. And nowhere is that more beautifully demonstrated than on Easter Island. For generations, researchers debated how the Rapa Nui transported their enormous moai from the quarry at Rano Raraku to ceremonial platforms across the island. Some moai weigh many tons. The largest completed examples are enormous. The obvious explanation seemed familiar. Perhaps they were laid horizontally. Perhaps they were placed on sledges. Perhaps they were rolled over logs. But local oral tradition preserved a very different explanation. The statues walked. For years, this was easy for outsiders to interpret as legend. Then researchers began asking a different question. What if walking wasn't metaphorical? What if it described the actual transportation method? Researchers, including archaeologist Carl Lipo and anthropologist Terry Hunt, have spent years investigating this possibility through experiments and analysis of moai design and ancient roads. The statues appear unusually well suited to upright transport. Many transport moai have features that allow them to be rocked from side to side while maintaining a controlled forward movement. Their center of mass and base geometry matter enormously. Attach ropes to the statue. Place coordinated teams on opposite sides. Pull one side, the statue rocks. Then pull the other. It rocks back. But because of its shape and forward orientation, each controlled rocking movement can produce a small forward pivot. Left, right, forward. Left, right, forward. The statue begins to walk. The principle is surprisingly familiar. If you've ever moved a heavy refrigerator or cabinet by rocking it from corner to corner, you've used a similar idea. Dragging the entire object creates enormous friction, but tilt it onto one edge, and suddenly only a small portion of the base is touching the ground. Pivot, shift, repeat. The object moves without ever needing to be fully lifted. Experiments with replica moai have demonstrated that relatively small coordinated teams can move multi-ton statues upright using ropes and rhythmic rocking. The hardest moment is getting the motion started. Once the statue begins rocking predictably, the team can establish a rhythm. Momentum begins helping. Each pull prepares the statue for the next. The people aren't overpowering several tons of stone, they're controlling its balance. And that distinction changes everything. Even the ancient roads may fit this method. Some transport routes associated with the moai are broad and shaped in ways that could help accommodate upright movement. Meanwhile, statues found abandoned along ancient routes offer another intriguing clue. If statues were being transported upright, a failed attempt could leave one stranded exactly where it fell or became impossible to move safely. A damaged statue might simply be abandoned. The journey ended there, and suddenly the old Rapa Nui description, that the statues walked, doesn't sound impossible at all. It sounds like an extraordinarily accurate description of applied physics. What makes this story so remarkable isn't simply that ancient people found clever ways to move heavy objects. It's that societies separated by enormous distances repeatedly arrived at similar underlying principles. Egypt, Britain, Rapa Nui. Different cultures, different landscapes, different materials, different centuries. Yet the problems were fundamentally similar. And so were many of the solutions. Reduce friction. A sledge moves more easily over prepared ground. Use water. Let buoyancy carry weight that human muscle shouldn't have to. Use leverage. A small force applied at the right point can control a much larger mass. Control the center of gravity. An object that cannot be lifted may still be rocked. Break one impossible movement into hundreds of possible ones. And above all, coordinate people. This may be the most underestimated technology of all. Human cooperation. One person cannot move a 30-ton stone. A disorganized crowd may not move it either. But dozens or hundreds of people pulling at the correct moment, following the same rhythm, using a system refined through repeated experience, that becomes something entirely different. The machine isn't made of metal. The machine is the group itself. Each person becomes part of a larger mechanism. One pulls, another stabilizes, another watches alignment, another prepares the path. Another supplies ropes. Another repairs tools. Another brings food. The engineering achievement is inseparable from the society that made it possible. This is why ancient monuments tell us more than how people moved stone. They reveal how people organized themselves. They show planning, specialization, communication, shared knowledge, and the ability to convince entire communities that some goals were important enough to require years, or even generations, of collective effort. The builders of the Great Pyramid didn't need modern cranes to think like engineers. The builders of Stonehenge didn't need trucks to understand transportation. The Rapa Nui didn't need motors to understand balance and momentum. Their tools were simpler than ours. Their problems were not. And that may be the greatest mistake we make when looking at ancient engineering. We confuse simple technology with simple thinking. But these were people with the same fundamental human capacity to observe, experiment, fail, learn, and try again. If dragging a stone failed, they changed the surface. If lifting it failed, they tilted it. If land was too difficult, they looked toward water. If one person wasn't strong enough, they coordinated hundreds. And if a statue weighing several tons couldn't be dragged efficiently across an island, they taught it to walk. The next time you see the Great Pyramid rising from the desert, Stonehenge standing beneath a gray English sky, or a Moai staring silently across Easter Island, remember what you're actually looking at. Not magic, not impossible lost technology, and not evidence that ancient humans somehow possessed machines more advanced than anything archaeology has discovered. You're looking at something more human: patience, observation, experimentation, cooperation, generation after generation learning how to make the physical world work in their favor. Rope became a machine, water became a vehicle, a ramp became a lifting system, a carefully shaped stone became something that could walk. Ancient humans didn't defeat physics, they learned to work with it. And with enough people pulling together, even the impossible could move, one careful step at a time.